Well, the goal of lesson 27 is to kind of dive into the exponential function. We've done the linear function, quadratic function, we've done square root, we've done a absolute value. So we're kind of just building it a little bit further along. And I just want to make a point in the notes before we go on to our first example. But what makes up the exponential function is the fact of, instead of having things like y equals x or y equals x squared, it's look right here. Basically, focus on the fact of that instead of having x as our base, now x is our exponent, and that's what makes it the exponential function. Is that your variable, your independent variable, is now up in the exponent as opposed to a base where it was to the first power and it was the second power, or it was cubic. Okay, so that's what makes the exponential function. And then I give you 2 points here of just realizing that depending on the base, the size of the base, if it's a number larger than 1, then your graph is increasing tremendously and very, very, very fast. And that's what all this very, very first one's all about. You have a asymptote sitting down here. That's very important to remember. You have an asymptote. Because anytime you graph an exponential function, you have to include the asymptote on the graph. Okay? Very, very, very important. But it's just realizing the domain is all real numbers and the range are just positive numbers. So if you raise anything to a power of x, you're always going to get a positive number coming out. Something to keep in mind. Okay? And then the other way around is if your base is a number between 0 and 1, can't equal 0, can equal 1, but something between 0 and 1, like a half or a third or 2/3, 5/6, then it's just going to be decreasing very, very, very fast. Again, the domain's still all real numbers, except in the range is still only positive answers coming out. So both of these are graphed in quadrants 1 and 2, keeping the y values always positive, but encompasses everything, so all the way across quadrants 1 and 2. Okay? And both of them obviously both have that lower boundary at the horizontal asymptote y equals 0. Okay? And just real quick, this page right here is just more emphasizing the fact that all the rules of transformations are applied. Same thing here as it's been doing before. Everything that's considered inside the function, inside is going to be up in the exponent. So if you see anything happening up here in the exponents, it's inside the function. So it's always your horizontal movement, left to right, shifting left to right, flipping left to right, stretching left and right, that kind of thing. Everything outside the function is what all this stuff is going to be to the front or behind it. It has nothing to do with up in the exponent, and that's all your vertical stuff. So going up, down, flipping from top to bottom, or stretching vertically. Okay, and that's always affecting the y values. Well, how example 1 starts out is they basically just want to, let's get back into just to basic algebra, going with the exponential functions, just using our basic properties of exponential functions. Okay, and with this first example, how we're going to work it is we're going to use that whole concept that if you have 2 exponential functions, if the bases can be equal, then the exponents have to be equal, because obviously the only thing that 3 squared can equal is 3 squared. All right, so the question is, obviously these bases aren't equal. One's 9 and one's 27. But can we create them? Can we rearrange them or rewrite them, manipulate them a little bit so that way they are the same? Of course we can. 9 is 3 squared, right? So instead of 9 being raised to the negative 2x power, all I'm saying is 3 squared is. 27, well, that's 3 cubed. So instead of 27 to the x minus 1, it's just 3 cubed to the x minus 1. Well, further going into our rules of exponent, if you have now one base, which is 3, it's raised and re-raised. Remember, we multiply those exponents. So this is 3 to the negative 4x. And then here, being very careful as I multiply this out, it's 3x minus 3, not 3x minus 1, 3x minus 3. Okay. So now I can come in here and say, well, if these bases are equal, these exponents have to be equal. And it's as simple as that. And then just solve for x. So move that 3x over. You get negative 7x is equal to negative 3. Divide off that negative 7, and you get x to be 3/7. And there's your answer. So the whole reason behind this problem was just realizing if the bases aren't equal, try to do some manipulations to make them equal. They won't give you this problem if one side was, let's say, 9 to the negative 2x and the other one was 8. Obviously, it's not. It's really, really hard to get 9 and 8 to be common based. So they're going to stick it to definitely something that you can work with. Okay. So let's try this again with here example 2. I've got a base of 8 and I got a base of 1/4. Okay, I can kind of see something, but let's do some work here for a second before we get into this a little further. I have 8 to the 3x plus 5. If one of my bases is a fraction, the other one's not a fraction, I would suggest making them both non-fractions, first of all. So the rules of exponents say that if I want to flip that base on the right, so if I want to write it as 4, do you remember what we have to do? We have to make that exponent negative. Because if I go back to the rule, if it's let's say 3 squared is the same thing as 1/3 to the negative 2. Or if I had a base of 1/4 squared and I want to take the reciprocal of that base, anytime I want to take the reciprocal of the base, I have to switch the exponent. Simple as that. Switch the sign of the exponent in order to flip my base. That's that property I'm using right there. Okay. So my exponent, since it had more than one term, though, I wanted to watch out and make sure I put the negative out front of a parentheses. So this is saying 8 to the 3x plus 5 is equal to 4 to the negative x plus 2 by the time I distribute that negative. So I flipped my base and switched the sign of my exponent. So now we can analyze this. Powers, what does 8 and 4 have in common? Well, they're both powers of 2, right? 8 is 2 cubed. Now 2 cubed is raised to the 3x plus 5. 4 is 2 squared, being raised to the negative x plus 2. Okay, so cleaning this up just a little bit more. So 2 to the 9x plus 15 is equal to the 2 to the negative 2x plus 4. At this point right here, I've got the same base, so I can just focus on those exponents. 9x plus 15, negative 2x plus 4. Let's do some math, flip some stuff around here. So 9 and 2 is 11x is equal to 4 minus 15, negative 11, or x is equal to negative 1. Okay, so let's take this concept and try example number 3. All right, and with this one, just looks like we've got several bases going on here. Okay, so we've got 7, 2x minus 1. Now pay very close attention to this because it's kind of a tricky one. This is 7 to the first times. Okay, and I'm going to go ahead and take the reciprocal of that base. So now 49, and I'm going to take the negative of that exponent. So negative x plus 1. Make sure you're writing a plus 1 right there, because if you're going to flip the base, you have to switch the sign of your exponent. And I need to switch all those signs if it has more than one thing up there. So now to recognize it's 7 to this power, 7 to that power, and 49. Well, obviously I'm going to leave the 7s the way they are. I'm going to write 49 as 7 squared to the negative x plus 1. So just one more time real quick. So 2x minus 1, 7 to the first, and 7 to the negative 2x plus 2 by the time I take that base, raise and re-raise, and multiply those two exponents together. Okay, let's focus here on this right. This is very special, because if I have a base that has one power and I multiply it by the exact same base to another power, do you remember, what do I do to those exponents? Do I multiply them? Well, no. I only multiply exponents when it's one base, like up here, one base that's been raised and re-raised. When I have two bases side by side, like x squared and x cubed, remember we add our exponents? So we'll get x to the 5th. So let's go ahead and then clean up that right side, really. So here on the left I have 2x minus 1, and on the right I have 7 to the 1 plus negative 2x plus 2. That's how I'm going to combine those two together on that right. So 2x minus 1 is equal to 7 to the negative 2x, and 1 plus 1 is 3. Okay, now the bases are the same. Let's focus on those exponents. Okay, move my x's over, move that constant over, so I get a total of 4x is equal to 4, or x is equal to 1. And there's my answer. It's a little tricky, but just realizing that right in there, multiplication sign, so you have to treat them separate. That was the big key with this one. Okay, it had a little bit of everything. You had to take the reciprocal of the base, so switch your signs. Then you had to multiply some exponents. You had to add some exponents. It's a pretty good problem on that one. Let's try example number 4.